The true adaptability is going to, because again, it's top down. You're like one agent and trying to control everything. And that agent, it's still constrained by the fact that it's trying to do things in a hierarchy top down. So you're not going to get the true adaptability. And here comes the magic. If you take a complex adaptive system to manage a complex adaptive systems, you get the best behavior. And here comes the framework. How do you do that? You need to apply a framework. You can't just have agents do stuff, right? You need to define the goals, and you need to define what governs, and you need to put in mechanisms to keep them away, to make them to stay away from the bad behavior.
Welcome to the AI in Manufacturing podcast here on Industry4.TV. I'm your host, Kudzai Manditereza. And in this episode, we're going to unpack an agentic AI framework for manufacturing operations. My guest on this episode is Gilad Langer, who is the head of digital transformation practice at Tulip Interfaces, and he's also a prolific writer at 𝗹𝗶𝗀𝘀𝘁.com. So, Gilad, I've been following your blog for quite some time now because I really find it to be, insightful from someone with a deep manufacturing operations expertise. But recently, you published a post that really grabbed my attention, where you sort of proposed a composable agentic framework for frontline operations. So our conversation today is going to be based on that, because I believe this is such an important topic that we should be having conversations around in the industry right now. So welcome to the show. And before we get started, I would like you to introduce yourself to our audience and tell us about your current role and your background in manufacturing.
Yeah. So thank you for having me. It's great to be on the podcast here. And thank you for reading my blog. Sometimes I write stuff and, I think, where is this going? But apparently, people do find it interesting, which I'm thankful for. So, a bit about myself. I've been in the industry around 30 years. I don't look it, but I do have a lot of gray hair. I started, so this kind of the interesting story that I actually did my PhD thesis back in the 90s as part of a European project that was the kind of the foundation for Industry 4.0. So we're talking 90s. There are the EU funded quite a number of different research in manufacturing. I worked together, if you're familiar with the German, the RTWH Institute in Germany, where that's part of the Industry 4.0, and a number of other universities. In fact, we also had members from the U.S., universities from the U.S., and it was really about things that we now call names like IIoT and multi-agent systems, etc. My specific research, and this is where it kind of was around taking, there were different emerging concepts about trying to say, how is manufacturing going to look at like in the future? We were thinking future 20 years. It's more than 30. I mean, it became 30 years, but we were envisioning a world that was, very in disruption, where manufacturing really had to be agile, like it's becoming today. With the disruption, with the supply chain disruptions and COVID and everything that's going on, where you can't just rely on the fact that you have a consistent market. Markets are changing, new products are coming to market much faster. You cannot rely on the resiliency of your supply chains. They have to be adapted. That was the world we're envisioning, saying, what are manufacturing systems going to look like in that future? And they need to be highly adaptive and be able to change very fast. We're talking 90s, where, the traditional MESs were just starting, where ISA 95 is being worked on. We already at that point thought about this world. And so that was really my research. It was what really we're trying to do is take a look at biological systems, chaotic systems like the fractal factory, and from my perspective, looking at social systems. How can we replicate some of the adaptability of these systems in a manufacturing context? That was really kind of the premise, and coming up with architecture, etc. And then around 2000, when I finished and I was working in university, and from my perspective, a bit too slow and it's a bit too bureaucratic. I wanted to test the waters in manufacturing or in the industry. So I left I went to work for, between 2000 and now, 25 years, worked for both integrators, big and small, software suppliers. So I worked for a number of different software suppliers, so Tulip being one of them right now in this space. And, before Tulip really was in I worked for another startup before Tulip, but it was just the traditional stuff. So, I became an expert in MESs and QMSs and all great things. Spent a lot of time in life sciences as well. So really immersed myself in all to do with, standards or regulation, etc. So I brought all that passion to try to change the world into this traditional world, kind of, for I would say 20 years, kind of hit my head against the wall, like, you guys are not doing it right. And then somewhere around 7 years ago, I realized that this Industry 4.0 thing it's becoming a thing, and we're starting to see change in the world. And then I opted to go and start looking again at these startups that are doing these things. That's kind of how I ended up at Tulip. And what is so interesting for me with Tulip is that two things. First of all, it is really a realization of some of the concepts that we had in the 90s. It's just, essentially, this is a platform that truly realizes some of the core principles and architectures that we came up with in the 90s around how you truly, how you support a truly agile, adaptable type of manufacturing system. So, and multi-agent system, by the way, was part of it. So in the 90s, we called them multi-agent systems, MASs. They were very crude. You're think about, the systems were a prompt, like you had a prompt, like a blinking prompt. And it was really not really advanced AI. A lot of heuristics, like if-then type statements. We call them expert systems. People would put in their expertise. If this happens, if this, kind of causality types and deterministic. But and then just to see how this technology has evolved is for me, at the end of my career, realizing some of these concepts. So for me, it's very close to heart, and I'm very passionate about it. But also, I bring some perspective that nobody really stopped to even consider. That's why, so for example, the artifact model that I talk about and the framework that I talk about, just really concepts from that time.
Yeah, absolutely. So, such a fascinating to hear, the backstory and your background in manufacturing, and it's very clear, your passion around this idea of self-adaptive factories, or kind of like an indication that this is something that you have been thinking about for a long time. And as you mentioned also in your article, that this is something that has really, grabbed attention of some other manufacturing thinkers like yourself. And the insinuation in your article and even in your introduction now is that we might be finally there. So what I would like to find out from you is what developments in today's digital manufacturing infrastructure and in AI or agentic AI are finally making this vision realizable.
Yeah. So the number one is the fact that we are in this place, in this time in history of manufacturing, where adaptability has become a necessity. I think that's one of the drive. You need some drive to change, otherwise we would never, right? Again, if you take a look at macroeconomics and the world situation right now, and then we won't get into politics, but there's tariffs, there's wars, we just had COVID. There's just a realization by companies, and by the way, of course, the fact that digital technology is maturing and the AI revolution has become a reality. All these things is causing executives in the manufacturing space to say, okay, this is time to change right now. We need to do something. So that is one of the things that's driving this change. Adaptability, is necessary. I mean, the companies have to, build new factories very quickly, adapt to new markets, deal with the supply chain, deal with unexpected events, that happen in the world. So that's driving the adaptability. And so when we look at adaptability, we say, okay, if we look around us, which systems are most adaptable? If you think about it, right? And one of the things is we as humans are actually very adaptable, and I always bring the the Darwin quote. Everybody thinks Darwin said it's the most intelligence of the species that survive. In fact, that's untrue. He said it's the species that is most adaptable to change that survives, that thrives, and that is at the core of what we're trying to do. In fact, back in the 90s, and again, I'm bringing the 90s, there was a movement driven out of actually Lehigh University in Pennsylvania. It was called the Agility Forum. Have you ever heard of the Agility Forum?
No.
You know, there was an Agility Manifesto that had to do with software, but there was an Agility Forum, and they actually put in, you know, like the world is, they basically stated the world is changing, it has to be super adaptable and all that. And they said the difference is that you have to it's not about just being able to adapt. You have to thrive in that constant change. You have to use the fact that you are so agile as a benefit, as a competitive advantage. And that is at the core of what you're trying to do. So how do you, as a company, you know, the companies that are going to survive, as Darwin said, are the ones that use their ability to change and adapt as a competitive advantage. And if you think about, you know, companies today that are doing that very well, Amazon as such, you know, and a few other examples, you know, one of the things that they do is they are able to move into markets that they were never in before, and very quickly, you know, be able to some even lead in that market. I mean, think, you know, simple stuff that they did, you know, Amazon Robotics is kind of in, you know, I don't know if you know, but Amazon Robotics, like the internal automation in their warehouses. They build their own robots, and they, you know, they put in the warehouses. You know, if you look at there's been a slew of companies in that space that have tried to kind of do warehouse automation, and none have succeeded as fast as Amazon. I think they acquired a company too, but you know, but that's part of it, right? But that's kind of the point. So how do you do that? Like, how do you, you know, how do you do this? Obviously, if you try to use the traditional methodologies and technologies, they're very rigid, and we know that. Like, you know, how long does it take to put in an MES system, a QMS system, an ERP system, right? And they are, you know, how do you do that? You basically you go to your plant, you create a blueprint of what's going on, you lock it. Essentially, says like, this is what we're designing for. We have, you know, we go into rooms and we have design, you know, review meetings to accept the design and lock it. You know, once you do that, you're done. You're basically, you shackle yourself, you put yourself in a cell, you basically, you know, imprisoned yourself, and there's just no way out of it, right? And that's at the core of a rigid monolithic system, and that's exactly not how to do it. So, you know, in order to be adaptable, you need to completely change that paradigm. Like, we're not going to go and do blueprints and lock everything. We have to accept the fact that, you know, we are going to solve something today, and tomorrow it may change, and then the day after it changes again. So how do you do that? And that's, you know, that's part of what we call composability, and composability has 5 pillars. And I don't know if you've read that article as well, but the first pillar of composability is bottoms up. You do things emergent, bottoms up. And when you do things emergent, you do things bottoms up. This agile iterative, meaning that you go solve one problem and solve the next one, that is a replication of how very adaptable systems in nature, social systems, that's how we work. That's how we as humans operate in a social system. We are essentially imitating the mechanics and the dynamics of systems in nature, in our world, that actually are very adaptable. And that's what it is. It's called emergent behavior. It's a phenomenon called emergence. That means that, you know, and there's many examples for that. One of the examples I bring is a plant. You know, you put a seedling in the ground and it grows. It does not have there's no blueprint for that, you know, for that plant. The plant doesn't look at the blueprint once in a while and goes, okay, now I need to, you know, have a leaf here. It's emergence. It basically, it creates a few cells and then creates cells again and cells again. So if you and it has a common goal, it's trying to get to the sun. It goes up, it's basically going for light. If you put something in the middle, if you know, the plant grows and you put something that you know is in its path, it will go around it. There was no blueprint for how to go around it. It actually just does that. That's adaptability. And it does that because it basically every step thinks about the next step and the next step. That's bottoms up. That's what you're trying to imitate in a manufacturing system, is how you deploy and build a manufacturing system.
Oh, yeah, absolutely. I mean, this is such a fascinating topic because also, for me, part of the reason why I'm so excited about agentic AI is because it's one of the reasons why I really, went into this manufacturing or industry 4.0 space, because, and this is also a part where, you'd say ignorance is bliss, because for me, I think I read a book by Stanley Davis. It's a 1987 book called Future Perfect, where he talks about this idea of mass customization, how you could actually, manufacture a batch size of one product, right, with these adaptable systems. But obviously, as I started to go into, manufacturing, I realized that there's so much more that needs to be done before we get to that point, to such an extent that I even lost faith that we'll get there. So kind of like the introduction of agentic AI is kind of like the reason why I'm so excited about it, because I think this is where things might finally, go into that direction. So maybe if we can kind of like get into an introduction of the framework that you proposed. So essentially, your agentic framework for composable digital solutions offers a structured approach for integrating multi-agent systems into manufacturing operations. So can you help us understand why having such a structured framework is important to begin with?
Yeah. So the important thing to understand here is, again, you have to think about the mechanics that I just explained and how we leverage those mechanics. That's what we're trying to do, right? And I'll go a little bit back. You mentioned the book Mass Customization. And I wrote another article which I call The Genius of the Toyota System, right? That the Toyota system, actually, if you look at it, they realized the nature, the nature of a manufacturing system being very complex. In fact, manufacturing systems as systems, without not necessarily, not only the software, they are classified as systems that are called complex adaptive systems. So they actually fit into a class or category of systems that are inherently in chaos. They actually are in chaos. Now, chaos is not a bad thing. Everybody, the word chaos comes from, biblical sense that there was no order in anything. In fact, that's not true. Chaotic systems have an order. They actually have patterns. And what we're trying to look at are these patterns. And so manufacturing systems are a class of systems. They're called complex adaptive systems. Other types of systems like this are, for example, traffic. So traffic is another complex adaptive system. Weather is a complex adaptive system. And within these complex adaptive systems, there are patterns, and they're good and bad patterns. So one of the things that you look at, you go, is this a pattern that's going to lead us to good, or a pattern that leads us to bad, right? For example, if you're starting to see, you know that from traffic, and I actually have a story about Africa, and I actually grew up in Africa.
Oh, wow.
So this is my story about the weather. So I grew up in Nigeria and in Kenya, in East Africa. And when I was a kid, very small kid, my dad, this is my dad used to sell agricultural equipment. So we went to this tribe in northern Nigeria, and my dad was showing them sprinklers, how to do the sprinkler to put, to irrigate the fields. And they brought the witch doctor, the witch doctor, and the witch doctor said, "I don't need this because I can do a rain dance." and he did his thing, and he did the rain dance, and he predicted that tomorrow, and they saw the sun tomorrow afternoon, it's going to rain. And believe it or not, it actually rained the next day in the afternoon. Now, why was he able to do it? Because he's an elder person. He has a lot of life of experience.
Yeah.
And it rain in Africa is seasonal. If it rains in the afternoon, it always rains in the afternoon, right? So every day it rains in the afternoon, which he knew because he has experience, and he smelled. He probably smelled. He saw the clouds. He saw patterns. So he, as a human, already saw the patterns that said, "Look, it's very likely that it's going to rain tomorrow, so I'm going to do a rain dance." He's proactive, right? But that's the point, right? In these systems, there are patterns that indicate whether things are going one way or the other, and we're trying to replicate those patterns. And what Toyota understood is that there are ways to impact those patterns. So, one of the things that causes in complex adaptive systems, if you push the system, if you take out the slack, and think about traffic, you put more cars on the road, highly likely that's going to be a traffic jam, right?
Yeah.
And it's the same thing in the Toyota. Basically, the whole idea of pulling versus pushing is a mechanism to keep it from getting into the bad. Because when you pull, think if you also did that on traffic. The problem with traffic is it's pushed because the car behind you is trying to get closer and closer, and the guy in front is not moving fast enough, or some obstacle. So if you pull, you get more flow, and you get less disruption, and therefore you get less bad things in the system. The other thing is remove the obstacles. Remember, even in traffic, if you put if somebody crosses the road or something falls on the road, like you go sometimes something fell off the car and there's something on the road, boom, there's a traffic jam. What you do in lean is you look for those obstacles and remove those obstacles as fast as possible. The and-on is meant for that, right? Yeah. So that is a behavior. If you remove that behavior, the system is not going to get into situations where it's bad. So again, they understood the mechanisms of a complex adaptive systems, and they put in methods and tools, lean methods and tools, to make sure that the system keeps in the orderly side, or behaves the way they want. So that's a complex adaptive system. And what makes a complex adaptive, and I'm getting to agents in just a bit, but a complex adaptive system is that it's made of discrete entities, right? It's a discrete system in an entity that follow a path, right? So they have a discrete entity follow the path. And that's what happens in manufacturing. Discrete entities are the units, the machines, the people in there, and they're moving stuff around. Now, if you take the agent part of it, actually, agentic systems also behave the same way. There are discrete agents, each doing their job, and they operate together. Now, they themselves are forming a complex adaptive system. And here comes the magic. If you take a complex adaptive system to manage a complex adaptive systems, you get the best behavior. Now, if you get a agentic system, which is complex adaptive, to control the complex adaptive, and you can manage, you can control the agents, then you have the best of both worlds. You have the adaptability that you need, but still you have a way to manage it in a way that it stays in a place where it's actually very effective. And here comes the framework. How do you do that? You need to apply a framework. You can't just have agents do stuff, right? You need to define the goals, and you need to define what governs, and you need to put in mechanisms to keep them away, to make them to stay away from the bad behavior. It's called a bad trajectory, I forget the word. It's an attractor. It's called an attractor in chaos theory. You have to keep them away from the attractors that are going to take them to a chaotic situation. It's a butterfly effect, right? The attractors that are going to cause a catastrophic event and keep them in the room, in the place where they stay in the orderly space, right? And the system behaves the way we want it to behave. And that's at the core of what needs to happen in agentic. Now, of course, the human aspect of it is you give people technology and they start building stuff all over the place with no rhyme or reason. Some people build good agents, some people build bad agents. And by the way, it's also important to note that agents themselves don't have to be intelligent. You can actually get the same impact with just agents that follow a simple heuristic, if-then statements. And you actually, and that's what we kind of started doing, before this agentic revolution. You just simply have, that in Tulip, the simple agent in a way is an app. An app helps an operator do something, a job on the floor, and it has some simple heuristics and through a certain flow. That in itself, by building small, apps helping humans do work, and many of these apps working together, you get the same behavior. What the AI does is basically it puts it into hyperspeed, puts all this into hyperspeed. It makes the system, infinitely more adaptable. Infinitely. Now, it's also dangerous. Yeah. If you don't have the mechanisms, if you take AI away and put this system in place, and it doesn't behave the way you want, if you then put AI on top of it, you're going to get super fast chaos, super fast situations where it just goes really bad. Think about a line down. If you have agents running, and here I'll give you another example. The apps that we use for navigation, like Waze and Google Maps, right? So Waze, before it was acquired by Google, they now they use sensors on street sensors and many other things. The input to the system is multiple ways, but at its core, Waze was a social GPS. It actually got input from people pressing buttons, going, "Oh, I see something on the road. Oh, I see a traffic," and they would monitor, how fast you're going, and go, "Oh, it looks like you're slowing down. Is this a slowdown?" They would ask you, and you would say yes, and then they go, "Okay, there may be a traffic jam here." So what they, one of the cases is there was a flood. A part of the road was flooded, and you couldn't pass through, and it looked green. So everybody routed there without knowing that it actually was flooded. So you had very, very quickly, it created a huge mess traffic jam because the input was incorrect, right? So again, you can, if you don't watch out, if you don't put a framework in place, things like that can happen. So you can very quickly get in situations you don't want in manufacturing, right? And hence that's what you need. And of course, there's the governance piece of it and democratization that we all know, right? You need to, you need to follow best practices. And if you're in the regulated space, you can't just let people do whatever they want. So putting a well-governed framework to how to manage technology is not uniquely AI thing or an agentic thing. It's just something that's good best practice. You just now need to fit the whole agentic AI thing into your governance, and the governance needs to accept and adapt to the fact that you have a complex adaptive system. You have, a composable system that is built bottoms up by people, democratized. Still needs to be lean, right? All that needs to be put in place. Otherwise, somebody is gonna, you give people technology like this, and guess what? You find somebody on the left that decided to replicate a monolithic rigid system, and then we wake up one day and they go, oh, look, somebody recreated an MES that's monolithic. What does that help? That's not helpful, right? So
yeah, absolutely. That's really exciting, because I think these problems in a way they reveal themselves, because that's also what motivated me to I recently wrote a paper around the idea of using sort of like a agentic MQTT as a communication framework or backbone for AI agent communication, because to me it was clear that as soon as people started to deploy all these custom agents all over the place, I mean in IT, OT, and they've got no way of exposing information to each other, and they've got these point-to-point integrations or going back to the same spaghetti architecture, siloed,
yeah, and that is so dangerous. It can actually cause very bad things to happen if you don't think about it, and if you don't think holistically, right? You can create a little sub-optimization. Oh, a guy can communicate, an agent does something. How do you know its impact, its effect on the rest of the system is good? Because it can be also on the bad. Take it a tractor to the bad and cause a complete shutdown of the plant sometimes, like fully catastrophic, like a butterfly effect.
100%.
And it can, and in an agentic world, in a technology like in a UNS with communication in real time, happening so fast, that can happen so fast in a blink of an eye. It's not, it's not paper based and people running around and there's some, oh, okay, I can stop the guy. Don't go do that because I can see you going to do that. This is happening in milliseconds, right?
Oh yeah, absolutely. All right, so maybe let's dive into the framework itself. Can you walk us through the the shared taxonomy that you've proposed? So you've got these different types of agents that you propose. Can you kind of like take us through the different categories and how they interact with each other?
Yeah, for sure. So the one thing we have to you have to think about agents as two things they can do. They can help you, like and the simplest way to understand what an agent is to say, like, imagine that you have a very good relationship with this university that is a top university. They only take the top students, and they educate them in anything you want. So you can go to them and say, look, I need 10 people that know everything about industrial engineering, specifically in my product, right? And I want them right now. And say, oh, here they are. The retrain. And now they come to you and you give them tasks. Like, I want you to go write me a design spec, and I want you to go, do a PLC program for me, etc. So really, agents are, in a way, you have to think about them as basically a staff. Like you can go and create as many as you want, and educate them in anything you want, and they actually do work for you, but you need to tell them what to do, right? So that's what really an agent is. So that's the one thing that they can do. The other thing that they can do is they can bring innate objects to life. They can take something like a piece of equipment, and you can wrap that piece of equipment with some level of intelligence or ability to communicate, to do something. Machines right now are innate. You have to go to them, set them up, and press a button to start them. And you maybe can put some automation where it does it by itself, but you can't chat with them. You can't talk to them and say, hey, I need you to go do something for me. So those are two things that agents can do for us, right? So if you think from that perspective, is okay. The first thing to think about is, in our world, just like any manufacturing plant, there are people who run the manufacturing, and there are people that help design the manufacturing, right? So there's an engineering organization. Their role is to create the line, or build the line, or build stuff for the line and improve the process. So that's one scenario where you can use agents. Sorry. There's another scenario, and that's the operations, the people running the factory, the floor, right? So first of all, we have to look at it that way. We have two scenarios. One is building, and one is operations. And that's, no big revelation here. That's how you run a plant, right? So therefore, we need to address those two needs, starting with that. Okay, what are agents that help us in the engineering space? What helps in the operations? Now, in the engineering space, there are two types of agents. One is called a staff helper. So this is like, you go to university, I need 10 people to write documents for me, and they come and you tell them what to do. Then we also have builder. In this new technology, we have builder agents. So you don't want to, I'm not going to write a PLC program. An agent is going to write a PLC program for me, right? An agent is going to create an app for me. An agent is going to create a dashboard for me, right? So these are agents that help us build the technology, the software and technology that we have, right? And then we have staff helpers. Write a spec for it, go test, I need you to test this new thing. So that's in the building space. That's not, again, nothing new here, and I think with many people that have agents to do this stuff. And when you go into the operation space, that's when it gets interesting. So of course, in the operation space, we have the help agents, the staff agents. I need you to go, monitor this machine and tell me how it's doing. I want to know what my schedulers are. Also staff agents, right? They're go do the schedule, monitor my schedule. The things that can help us do it. So take every operator and every supervisor on the shop floor can basically have an army of agents helping them do the stuff that they do, right? For example, an operator can have an agent that monitors the key component that he's using and saying when you need to go replenish. Like, just think about a Kanban agent, right? Oh, don't worry about it. I don't know. I use Amazon Pharmacy, another one of these disruptive things. I get a text saying, "Look, it looks like you're low on this prescription, and the doctor has not refilled it. Do you want me to go and ask for a refill?" Great. That's I have a staff agent helping me do it. The same thing can happen in manufacturing, right? Now, here comes the interesting part in manufacturing. It really is the adaptability. Is now we can now start. That's one thing. But now let's think about that that Kanban card thing. So now we have an agent. We can replicate, but the material can be an agent. So let's say we have a class of components that are critical, and we create agents for each one of these components. And you have, before you pick this component, before you take the sub-assembly in, you can ask it, when have you been tested? What's the test results? Are there any defects on you, right? And do you fit into this product that I'm building? You're chatting with an innate piece, an innate material, right? So you can do that with a machine. You can do that with your lot, your batch, right? You can also put agents around your systems. So you have each PLC is now an agent, right? So now we're taking the physical and operational artifacts in our world, and we are basically saying these are agents, and we can chat with them. So now that's one thing. The other thing they can chat with themselves, right? So I have a machine and I have a part. the part will go to the machine as an agent. You don't have to get anything. They'll go, oh, I am part A, and according to what I know, you could process me. Are you able? The machine says, well, just wait a minute. First of all, I need to finish what I'm doing, and I have a tool that's worn down, and I probably want to go get that that tool replaced before I did. So now you have that. It's agent-to-agent communication essentially, but you're this. But it's more than agent-to-agent communication because you have innate objects. Like you have essentially a factory that you can orchestrate. They can actually talk out of the automation space. These things are talking to themselves about that. And this is very futuristic, but that's where adaptability is. So you basically, you have a multi-agent system, which is your plant itself that is actually managing how to produce. And so that's the interesting part of the agentic framework that you put in, which is at the core of some of these frameworks. So that's kind of the future, but that's why it's so interesting.
Yeah, absolutely. I mean, it's one interesting approach that you took with your framework, which I found interesting, is this idea that you're looking at it from this idea of an agent being a digital twin, as it were. And this is, different to some approaches that I've seen. Maybe it's the same thing. Maybe you tell me, because some people would have an agent, say, they would have an availability agent or a quality control agent. So you'd have one agent that is calculating the availability of multiple machines, or one agent that is calculating the quality of multiple machines. So it's a different way of looking at it. So for you, you're saying each discrete item should have its own agent that is a digital twin that reports on everything about it, quality, availability, and everything in that one agent, which I find interesting.
Yeah, that's the premise. So it's not that the other thing is bad, and you should also have agents that are overseeing. So things, and it's natural. I think the agentic technology is going to the speed of innovation here is immense. So right now we are just at the beginning, and there's a lot of constraints, and so it's not bad to do that.
Yeah.
To do these things, but the power. The true adaptability is going to, because again, it's top down. You're like one agent and trying to control everything. And that agent, if you put a human instead of that, a human is able to do that. Agent just does it a bit faster. It's still constrained by the fact that it's trying to do things in a hierarchy top down. So you're not going to get the true adaptability because it's just one controlling everything, right? That's just a typical hierarchical top down. The true adaptability comes from you want to build and use the true, the mechanisms that I just described, this emergence, by creating a system that is made up of discrete entities. That's when you get that adaptability, right? That's when you go, because if you think about top down, you have one agent that does to control all the multiple machines to, let's say schedule, etc. That agent does something wrong, everything breaks. Like if it does not do its job, nothing works. If you do it the other way around, where you actually have agents per machine, even if one of those agents does something bad, or you just even close it, you say like you're away, it does not impact the rest of the agents. They can still keep going. In fact, they will adapt. They go, oh, it looks like machine C is not here anymore, and they will adapt. Right? You see, that's what we're leveraging the core dynamics of agentic, of multi-agent systems, and essentially complex adaptive systems. That is what makes us as humans. So I think about it from a human perspective. I give an example. When I used to give these talks, back in the 90s, early 2000s. I just you sit in a room, right, mm-hmm. and think about how everybody has nobody really knows each other, but we're all agents, and if we have an event, let's say the fire alarm goes on in that room, without any preconceived plan or anything, we will be able to remediate. We will all stand up and help each other and get out of the room.
Yes.
That's a true adaptive system, right? It's not. No. Now, how do you, if this was a manufacturing system, by the way, if you then say, okay, you now are you are not people, you're parts of a manufacturing system, and we apply the rigid monolithic thinking, ISA 95 thinking on this. Basically, you have a blueprint and a plan. And if fire happens and we did not program the scenario of a fire happening, we're just going to sit in the room here and wait to be burned. We will not do anything. We'll just sit. because we have no contingency for this thing that just happened. It wasn't programmed into the system, right?
Oh, yes.
And so that's how we run manufacturing. We run manufacturing like that. And as soon as an event that we didn't expect happens, we just keep doing what we're doing. We just sit there and burn up alive, essentially. That's what we do, right? Now, of course, humans step in and, you know, try to move people around. So like in this scenario, you know, the supervisor and the operator is going to start taking one person at a time. Go, you go, you go out, you go this way, go out. It's not fast enough, right?
Oh, yes, absolutely. Yeah, so one of the concepts that you bring into like this agentic framework is the idea that these agents need to be, anchored, for lack of a better word, anchored against this artifact model. So I think you sort of like gave us an introduction into this idea of an artifact model. But for those who may not be familiar with what exactly we're talking about here, so maybe could you start by introducing or describing to us what an artifact model is, and then explain how that fits into the composable agentic framework?
Yeah. So actually, it's at the core. It's at the fundament of this agentic framework. So when we think about how do we? It's essentially a data model, right? So how do we look at what we have in manufacturing? And so we have many different types of data models. ISA 95 has data model, etc. So the approach that we've taken so far traditionally is we have a database, an entity relational database, and we need to model the world into this entity relation data model, right? And that's at the core of everything that we do. All systems work that way, etc. But it's constraints because of the constraints of entity relations and kind of this translation that needs to go on. We kind of end up where we ended up. It also causes, it's not democratized. These models are very complicated, and so for people to go in and take a look at that, they need expertise. They need somebody who understands the model and somebody who knows how to do SQL and data science and all great stuff, right? And that hinders the value of the data. One of the things with digital technology is that the premise is that you get insights into your manufacturing that is that helps you become more productive, right? Really true insights. And in order to get those insights, you cannot have data that requires you to ask somebody to go do a report for you and put it in a PowerPoint that you can look at it or once a week, etc. You should be able to go into that data and look at it and go, uh-oh, I get what's going on here in this. So we need to start looking at data, from a kind of, think about knowledge graphs, etc. So knowledge graph is about how do we take our perception and perspective into data and kind of help us analyze the data, meaning like we put true relationships, not entity relationships, but relationships that make sense for us. And in order to do that, we need to also reflect on the data model. So essentially, the artifact model is just a way to structure your data in a way that is human consumable and uses human into it. Like we can do something with it, and also is ready for AI and ready for to more effective with knowledge. So how do you do that? First of all, simplify. Like we need it to be much simpler, right? So traditional data models are way too complicated. One of the things that makes them complicated is that they try to put the transactional piece of it in, right? There's things like machines and materials, but we also need to model the transactions that we do on them. How do you move them, and how do you produce them, etc. If you take that and say, okay, we don't need to do transactions that the agents do for us, right? In our world, the apps, the agents do all the activity on it, humans as well. We just need to replicate what we see on this, what do we see happening on our shop floor, and be able to do essentially a true digital twin kind of thing. So that's the premise. And actually, it is pretty simple. If you go to a manufacturing plant, okay, and again, this stems from the research we did back in the 90s. We spend a lot of time in thinking about how do we create these true digital twins? What do you have in a manufacturing plant? We looked at many different standards and models, etc., from different perspectives. Like look at it from an operational perspective, and look at it from an operator perspective, and look at it from a design perspective, from an engineering perspective. You know, the example is, you know, I have my coffee cup here, right?
Yeah.
How do you model a coffee cup? If I'm a you know, let's say a process engineer that needs to make this stuff, I say, well, it's a solid. It's a solid that I put a hole in. Like I made a hole in the solid, right? If I'm a design engineer from a usability perspective, I'm thinking about, oh, it's a container with a handle that's easy for me to catch. Like I'm looking at the handle. Right? So everybody has a different perspective on how you model a system, right?
Yes.
And so, you know, the perspective we're taking is a kind of a unified perspective and say, okay, like what do you have on the shop floor? Okay, so let's start with the simple, right? And at the core, like we have machines, right? And then we have materials that have to be processed by the machines to come with a product, right? So there's a class of objects that is physical. There's a physical thing on the shop floor. We have a machine, and we have a room or a area, right? Those are called physical artifacts. We have and we have materials, you know, raw material. But those are, we call them physical artifacts. So those are things that I go to the shop, I can touch and feel them. I can touch and feel a machine. I can touch and feel a person. I can touch and feel a material, right? Those are called physical artifacts. So that's one thing that you have on the shop floor. So the first thing you do is classify things as either physical artifacts, and the other is operational artifacts, things that we do with. So an order, it's not something physical, but you cannot, in a shop floor, you need an order. You need to produce against a demand, that's an order. A defect is a representation, and something is a task or an event is an operational artifact. Now, if you take those two things, physical and operational, you will find that there's no more than a handful of different things in a manufacturing site, right, that can classify that. Anything else is actually, we don't think about it right now, right? So you have your machines, your tools. You think about it: machines, tools, a room, an area. You can't come with much more than that. And then there's direct materials, raw materials, the semi-goods, sub-assemblies, final product, right? Those are the truly, that's it. And if you go to any manufacturing plant, you will typically see that they will come up with 10 different physical artifacts that they have on the shop floor. That's it. And that's manageable for humans. And that's what you need to represent in your data model. Your operational and your physical artifacts. And that's at the core. So if you represent that in a data model, and it can be unique. I mean, even though, for example, you have a CNC machine and a testing device machine, you know, 80% of the attributes of those two things are common. So you can create like a common template for what is a machine artifact or a resource. But then you can have different, if you will, tables for your, you know, your I don't know, DMG Mori CNC machines, and a different table for my Mazak machines, and a different table for my, I don't know, custom test devices that I use, right? But the tables actually look very much alike. The data columns are more like there's maybe a few more columns that are unique for them, but you know, you'll find a lot of commonality. So you need to manage that. But that's essentially it. And it becomes very, very simple for somebody to walk in and look at this data model and go, yeah, or here's my DMG machines, and here are my Mazak machines, and here's my, you know, you're basically looking through a spreadsheet and going, yeah, I know what I'm looking at, right? That's at the core of the artifact model. And if you basically design your data model this way, first of all, it's super simple. It's democratized. Everybody understands it. And it's easy to put knowledge graphs on them. Why? Because it makes sense for us as human, right? And the relationships between these things are inherent, right? They reflect the reality of the shop floor. It's not not a complicated abstraction of something that you need, right? So it keeps that as, and I typically say that the complexity of the system that you know, your digital twin or your system that you use should never be more complex than the reality, right? So if you're going in and you say, okay, I have a few machines and I have my process here, and you look at the data model, and that data model is super complicated, it's more complicated than the production unit you're doing, then you have something wrong. And not to say manufacturing can be pretty complicated. Now, sometimes the complexities are high, but that's why we have engineers. That's why manufacturing is run by engineers. But the data model needs to reflect that complexity. It has to be one-to-one.
Yeah, absolutely. So the idea is that then that becomes that source of truth, as it were, for the AI agents as they interact with each other. That artifact model.
Yeah, exactly. So it's then easier to create the agent on top of it, right? Because I need a machine agent. Well, here's the data for machines. Like, you own a row in that table. That's yours. That's everything you are. And then, of course, there's all the data. I mean, you have a lot of history data that's captured, right? And that history history data is captured in kind of, if you will, in flat files, right? So if you think about UNS and historians, they captured very flat types of data. Like, it's just basically redundant data about what happened to that artifact. What you want to be able to do is like, okay, here's my artifact, and here is you can take the ID, the asset number of that machine, and then go into the wealth of logs that you have, your UNS hierarchy and your system logs and what have you, and you just go, look, I need to get all that data about me. So the agent has a way to go get his history of what's going on and understand what's going on and look at patterns within that history and say, oh, it looks like I always fail when this operator uses me. And now I know that as an agent, right?
Oh, yeah, absolutely. So, I mean, you've already done a great job of really, helping us sort of like visualize what, the future of manufacturing could look like. Maybe if you could like kind of like condense that information for us on what kind of like do you see as a typical, factory with the enabled by multi-agent collaboration frameworks, and maybe if you kind of like put it in comparison with how we currently do, approach this continuous improvement and automation.
Yeah, I know. Therein lies the challenge, right? Because these concepts in theory are easy to understand, and the impact is really understand, again, because we can reflect on things that we know, things that we live in everyday life, the examples I gave with traffic and weather and such, right? So, that's easy enough. The reality is, plants, first of all, walking into any facility, the average age of equipment in a facility is typically around 25 years. So, looking at systems and there's old stuff there, and nobody's going to go, cool, we want to use all this new agentic stuff. First of all, we're going to replace all the machines with new machines and put in all the new systems, etc. Nobody does that in manufacturing, and it's kind of a step-by-step process. But the good thing about composable technologies is that you don't have to do, it's not a one size, it's not a big bang type of approach. Pillar number one of composability is do things bottoms up, iterative. So just start somewhere, like go somewhere in your facility and start doing this and let it grow from there, right? So the good news is you don't need to apply agents everywhere. You can start small and build. In fact, that's the only way to do it properly. And that's how this technology works best. So that's the main message to most people, most companies that are going to this space. The good news here is, true Kaizen. Do a Gemba walk. Find a place where you want to start and start there. And it doesn't have to be greenfield or so. You can go and say, I have a piece of equipment here that is very critical for me. It's 25 years old. It doesn't have even, it's like, I can't even connect to it because there's some relays and nobody wants to open that panel because, it's been locked for 10 years, right? And make it smart, put some sensors on this machine, create a simple agent for that machine. You create your first machine agent, right? You don't need to create agents for everything. It's one machine agent. Give it a go. Give it some instructions of what it needs to do, right? And start connecting it. The UNS is kind of the same thing. Get some data out of that machine. Put an agent on this, right? And then have operators interact with that agent and see how it goes, right? Again, you're building. Build an app for that operator that allows him to do his work, that connects to that machine and lets the machine interact with that human. So basically, that agentic machine now can tell a human, look, not only am I down, but I have some reasons for it, and in the past I know it. I just basically go check Now go check on, on the left side of this, usually something gets stuck there and that's why I'm down, right? So it's using the human to help itself, right? And just you go from there. Okay, that went well. And then, go on from there. Now, of course, that first machine is easy. It's just a quick agentic machine and you do something. But then, as you go into the next machine, etc., you need to start thinking about what we talked about before, governance. And how do we control this and all the other things. But again, even the governance that you need to put in place, that also kind of grows with time, right? You don't need to put a complete governance for all of your plant just because you're going to do a test with one machine to create an agentic. Like, just do that. And then, step by step, you can go that. But I think, so that also is pretty straightforward in what you want to do. The biggest problem in all of this is the mindset, is the culture shift that you learn. Because, even if people buy in, so if you take, let's say, you go to a company and there's a few engineers that subscribe to this and actually want to do this, if you don't watch out, they very quickly will, because of the way we're educated, the way we've done things in the past, we will very quickly start falling into the monolithic very quickly, and I see that happening all the time. They'll build the first app truly composable. And then you go, okay, this is going well. And you come back a month later and they build a monster monolith the old way, right? So that's why you have to think about, so governance is also about culture. You need somebody to kind of be the change agent to hold them to the feet to the fire and go, look, you did that very well. Like, how do we move on, right? It's the same thing that happens in a lean kind of transformation, right? The lean sensei comes in and kind of guides, it's the analogy, the wax left, wax right analogy, right? You need to get that muscle memory in and keep doing it the right way all the time. And I think that's the hardest part of it all, to create that culture, that change culture in an organization that doesn't go back. I'm not talking about, just dealing with the transformation as a whole, explaining in a regulated space, explaining to the quality people that they have to think differently and things are going to change. How do you keep compliant? I mean, I am glossing over a depth of complexities and problems and challenges in manufacturing, that are there, and that's my everyday. I mean, I go to customers and it's this change. People don't. It takes time, and especially in a conservative industry like ours, it takes a lot of time.
Yeah, absolutely. So, I mean, I don't want us to close this conversation yet before we talk about more the practical aspects of this, specifically with the platform that would then allow you to, operationalize, the governance and the composable agentic framework that we spoke about here, which is the Tulip Interfaces already supports this, kind of composability and AI agent building. Can you kind of like just, maybe for those who may not be familiar with Tulip at all, just quick explanation of what it is, and then talk about how that enables you to operationalize this framework?
Yeah, so Tulip is what we call a frontline operations platform. It's it's based on no-code. It's a no-code platform that allows you to build contents like agents and other, and apps to help support your manufacturing plant in a composable way, right? So it allows people in a no-code environment that don't need to know any software to create content for your shop floor. Everything, connect your machines. Build user interfaces for your operators, like work instructions or material management, and all the different use cases that you have. But the premise of Tulip is that it is inherently composable by nature, meaning that it was built from the ground up with this new thinking in mind. So what in the space that we talk about, it is the operating system for it basically is the modern operating system for your shop floor. It is the platform that allows you to really bring these concepts to life. And because it is a platform, it gives you the tools to put in the governance that you need. So to make sure that people are building the right thing, they do it in the right way. Everything from simple stuff like they're even allowed to do this, to allow to build an agent, right? I mean, that's just simple governance you need to apply. And it's important. And one of the things that to realize and understand it's that when you look at trying to realize some of these concepts and using these technologies like agents, you have to rely on systems that were built from the ground up with that in mind. You can't just go and say, look, I'm going to use my traditional MES and do agentic. It does not work. Those are systems that were built from the ground up, basically the exact opposite of agentic. They were rooted in monolithic structures, which was the name of the game in the 90s, right? So you can't if you have an infrastructure infrastructure that only allows electric vehicles, you can't get a bicycle on it. It's like, it's for electric. Horses and carriages just won't work there, right? So you have to think about it that way. And another blog post I wrote is, how do you determine whether technology or platform is composable or not? And basically you use the 5 pillars and you ask that question. Is it going to support bottoms up? Is it going to support lean, my lean improvement? Is it democratized? Is it human-centric? Is it compliant? Just ask those simple questions and you will get an answer whether you truly have a platform that allows you to not only enable this multi-agent system and the agentic and everything that you do in a composable way, but it's going to take you to the promised land, order of magnitude productivity increases, which is the true, why digital is important for us, right? And it's a simple thing. Like, people ask me, use the system. I say, how long is it going to take you to? And let's say we want to. The example we gave him with a machine, like how fast can we get this machine connected and an agent created on that machine, and we can start seeing benefit. And if they say months or more, it's not that. The answer should be hours. Like, can I, true Kaizen, right? I go do my Gemba walk. I find that this machine is not working. Right there, roll. The story with Toyota is roll up the sleeves and fix the machine. Can we do it within an hour? If you can do it within an hour, you have a composable platform. If it's I need to install, I need to do this, I need to create master data, then you don't have a composable system.
Yeah, absolutely. Gilad, unfortunately, we've run out of time, but this has been such a fascinating conversation. Thank you so much for taking the time to share insights with our community. We'll certainly provide links to your blog and also to the Tulip website for those who want to check it out. So again, thank you so much and really appreciate it.
Thanks, Kudzai. Great being on the podcast here. I appreciate it.